I'm very privileged and thrilled to introduce our first speaker of the day, Dr. Chen-Ping. I think he's the founder and then CEO of the company Phiar. I think it's pronounced as Phiar, but it is spelled as Phiar. So it is. I think the area they're working on as a company, he's actually driving this, and it is one of my interesting areas as well, because how many of you are lost when you're navigating through these busy streets of San Francisco or New York and any of these big cities? A few. And then, because when we drive through these cities, we actually see through them. We see through them and we feel sometimes, hey, we are able to see this, but the damn GPS system or the smart system, even though it is smart, it is not that smart enough to really understand what am I looking so that it can really give me some meaningful way of navigating. So that's what I always used to think, hey, is there any way to link what I am seeing to the device so that it can intelligently give me a way of navigating through these challenging streets? So this is one of the challenges that I always had in mind. I'm really happy that Phiar has a solution, and they are the first in the world to come out with a solution that addresses this exactly the problem. And I'm greatly thrilled to actually introduce Dr. Chen-Ping for this particular session. And then he's going to talk about some interesting elements related to the approaches that we have in the computer vision and also the deep neural networks, because we all have been through this process of image processing using convolutions, different type of convolutions, but we know there is a lot of data. But there is a new concept. It became into live more on the MobileNet side when they came out with this depthwise, separable convolutions. So he's going to talk more on the separable convolution techniques and how it is implemented in today's computer vision and also the deep neural network approaches. And it's going to give some insights into the use cases so that it can be benefited. So please welcome Dr. Chen.
Hello. Hi, everyone. Thank you for the warm introduction. Hopefully, more people get lost when they're driving in San Francisco, because that's our use case. But my name is Chen-Ping, and I'm the co-founder, CEO of Phiar. Today, my talk will be about separable convolutions for efficient implementation of CNNs and other vision algorithms. So first off, let me reintroduce our company a little bit more. What we're working on is AI-powered AR, augmented reality navigation platform for driving. Our first product is augmented reality navigation, a mobile app that you can download on your iPhone. The reason why we're building that is because, take a look at the screenshot that I took when I was in Boston on the lower left-hand side. That's Google Maps showing me where I was and where I needed to go. I looked at that. I had no idea what that meant out of the 10 streets in front of me. I looked up in front of me, still no idea. Had to make a split-second decision because you're driving and ended up making the wrong turn. So that was a pain point that we're going after because we thought navigation is something every driver pretty much uses all the time now. But we're still using a 2D map. However, people already mount their phone with a mount on the dashboard or the windshield, so the camera is already facing forward. Why don't we show people the live camera feed, and overlay your route directly onto that live feed so that all it takes is a quick glance. You'd immediately know where to go, and you'll never make another wrong turn, miss another exit, never be confused. You don't have to read maps anymore. But to make that possible, there's a lot of on-device computer vision we have to do. So that includes road understanding AI, SLAM, path planning, so object detection, lane segmentation, semantic segmentation. Everything has to work on the phone, real time, all together on device. So that's where separable convolution is an important part of making that possible, and that's where I segue into my talk today. So our agenda today is I'll start with a bit of introduction of what spatial convolution is in computer vision. Then we'll go into what separable convolution is, which is an extension of that. And several applications in deep learning, how they've used separable convolution. One is called low-rank filter expansion. Second one's flattened CNN. And the third most popular one, MobileNets. Finally, I'll go through some considerations and takeaways of how we can really use separable convolutions to our advantage whenever you're building an efficient, fast, lightweight neural network. Okay? By the way, the timer hasn't started, so. Thank you. First off, spatial convolution. Spatial convolution is very old, and let's go through that. I'm sure most of us are familiar what spatial convolution means. Is that when you have an image on the left-hand side, and you have a filter or a template on the right-hand side, what you do is you perform a sliding window to slide that template along the image by center aligning the center of the filter with respect to every pixel on the image. And then you perform dot product. So what are the two biggest use cases for spatial convolution? One is smoothing. So if you have a Gaussian filter, you smooth an image. The output image is smoothed. The other big part is template matching. So template matching means finding something that's similar in the image to the filter. So let's dig into that a little more. Given an example of an input image that we label F, we take out two crops of that image. One crop is the corners between the windows, and the other crop is the trunk of the tree. And the task here is we want to find those things in the original image using those two crops. And that's what we can use convolution for. So we convolve the image with a filter, K, and wherever the matches happen, that would be the highest response area. So if we convolve the corner of the windows with the original image, you see that the response map shows up really bright at where the images are most similar to, the pixels are most similar to the filter. Likewise, if you do that with the trunk of the tree filter, then you see that the highest response is actually at the trunk of the trees, the three of them. But there's some caveats. It only works if both F and K, the input image and the filters, are normalized. By normalized, I mean they have a zero mean and unit standard deviation. And that's what people do with neural networks today as well, where you want to normalize your input image so that everything's is zero mean and standard deviation, unit standard deviation. And what this technically really is actually something called cross-correlation. Because a convolution means you have to flip the filter horizontally and vertically. But in today's world, cross-correlation and convolutions is used interchangeably. So from here on, I'm going to use the term convolution and to mean the same thing. So some in-depth example. Let's go through spatial convolution once. If we have an input image F and we have a filter K, we want to center align that filter with the pixel that you're processing around it. But here, when you center align, you went out of bound because there are pixels that's non-existent with the outside boundary of K. And that's where you pad it with zero. So that's why it's called zero padding. And what happens is you perform dot product. So that's it's a 3x3 filter, and therefore there's 9 multiplications, element-wise multiplications, and you sum them all together into your final response of that, the convolution of that filter at that pixel. Then you slide it to the right by 1 pixel, and that's what's called stride equals 1, because you're moving 1 pixel at a time. Compute the same thing, move to the right. After you finish the first row, you go to the second row. Okay, so that's pretty straightforward. But just remember how many multiplications happened per pixel here. It's based on the size of the filter, and in this case, 3x3, so it's 9 multiplications. Okay. So for separable convolution, what that means is we can actually decompose a 2D filter, K, into a sequence of 1D vector convolution. So as shown here, it can be decomposed into a column vector that's convolved by a row vector in 1D. And what does that give us? But maybe we should go into why it works first. Okay? This is also equivalent to outer product or matrix multiplication. That means if you perform matrix multiplication on those 1D vectors, you will get exactly that to the output. Okay? And this 2D filter is something called Sobel filter that's often used for edge detection. Okay, so let's dig in just a little bit technically about why that was the case. So convolutions has associative rule, which means when you're convolving a bunch of things, the parentheses can move forward and backward, and that makes things still the same. So given that, and we already know that a 2D filter K was able to be decomposed into a column vector convolved by a row vector R. And from the first image, we were convolving a filter K with an image F. And we're just copying that, right? We substitute K with C and R, and therefore the right-hand side becomes F convolved by C convolved by R. Now we apply the associative rule. So we can move the parentheses from the right-hand side forward for a little bit. And since that the parentheses now happening in the first part of the equation, then you can just take the parentheses out. It's still the same thing. And that means what you got is by convolving a 2D filter with an image, you're getting the same result if you convolve an image with a column vector followed by a row vector. Okay, so this is what's illustrated here. A picture illustration, same thing. If you convolve a 2D vector with an image, you get a certain result, and that gives you exactly the same thing. If you convolve the input image with a column 1D vector followed by another convolution of a row 1D vector, same thing. So now we've established that a convolution can be separated into 1D filters. What does that get us? Why is it reducing complexity for us? So let's take the first case, convolve with a 3x3 filter. Remember we talked about there's 9 multiplications per pixel when you center align a filter with an image, with a pixel on an image. So let's say that this filter is 3x3, but let's just to make a more general case, let's use n to describe the side of the filter. Then in this case, if you're convolving a 2D filter with an image, per pixel, there's n times n amount of multiplication. In this case, 9, but in the runtime case, big O notations, n squared. If it's a 3D filter, which is likely the case for neural networks because you have X, Y, and channel, then the runtime per pixel of filtering takes cubic amount of multiplications based on the size of the filter. So that means if your filter is larger, it takes even more computation. And that's why most neural networks stay at 3x3, because that's the smallest that they want to get to. Now, if we move to separable convolution, something interesting happens. First, you're convolved with a column vector, and that's 3 multiplications because there's only 3 elements when you're center aligned to a pixel. And then when you do your second step, which is convolving it with convolving the result of that with a row vector, that's another 3 multiplications because that's a sequence of convolution happening. So it's 3 plus 3 rather than 3 times 3. And in that case, a 2D filter, 2 1D filters become linear time of runtime. And even in 3D, if you decompose them into 3 1D filters, it's still a linear time operation. So now the difference is very apparent. You drop from cubic time to linear time. Okay, so that's the importance of separable convolution here. Before I go to deep learning, I'll give an example of a non-deep learning example of using separable convolutions. This is also one of my previous work in 3D tumor detection. The input is a 3D MRI scan of your brain, and the task is to automatically detect and segment tumors in your brain. What we found is that tumors are blob-like structures in your brain, and so we wanted to use a filter that detects blobs, and hopefully then that can detect tumor for us automatically. And there is a blob detector called Laplacian of Gaussian filter, and that looks like a Mexican hat. So you can see that it's looking for a blob-like structure from the input image. But when we run this in 3D, that Laplacian Gaussian filter becomes a 3D filter. And like I said, that's very, very expensive to run through a brain scan. So what we did was we decomposed that into a sequence of 1D filters, which has the following formulation. And the result is we were able to segment and detect tumors automatically with the same high accuracy, but much reduced, much faster runtime. So here are the statistics. The head MRI scan has a dimension of 256 by 256 by 256, so a lot of pixels to run with. So remember, you have, if you're computing a native 3D convolution, not only you have n times n times n amount of multiplications per pixel, then there's 256 cubic amount of pixels to run that with. So that's a lot of computation. And that ends up to be more than 2 hours of runtime. But if you separate it into 1D separable filters, exact same results, but less than 2 minutes. So that's the type of speed up you're getting. Okay, now let's go into deep learning in terms of this use case, in terms of separable convolutions. The first example I'll go through is a work called low-rank filter expansion, and that was published by a group at Oxford in 2014. What their idea was that they're going to pre-train a network, a regular network consists of 3D filters, but then they're going to reconstruct these 3D filters with consists of 1D and 2D filters. And they had two approaches. The first approximation approach was to use purely 1D filters to reconstruct those pre-trained 3D filters in a network. The second method is to use 1D filters followed by 2D filters. And those results, what they showed was that they trained a 4-layer CNN, kind of small, and they evaluated on the text recognition data set. They demonstrated that the speed up was anywhere between 2.5 to 4.5 inference speed up, with less than 1% accuracy trade-off. The issue here is that they pre-train something, and then they have to reconstruct it. So that seems to be something of an extra step. So the next work that I'll go through is to skip that extra step and directly train network with 1D filters. And this work is called flattened CNN. Excuse me. Flattened CNN was published in 2015 from Purdue University. They trained a network from scratch with a sequence of 1D filters, exactly as I've described in the 1D separable case earlier on. But their ordering was that they first start with a 1D filter along the depth, along the channels of the network, followed by the row, followed by the column. Okay, so they do the spatial side after the channel side. Their network was 5 layers. So there's 3 convolutional layers consist of 5 by 5, and then 2 fully connected layers. And the important thing here, what they found to work was that you have to, compared to their baseline 3D filter conventional neural network, they have to swap out 1 conventional layer with 2 sets of separable layers. So you have to do twice of channel, row, column, and then another channel, row, column. And that substitution got them the 2 to 3.5 times speed up and at the same or better accuracy. What's interesting is that they want to show this kind of a training, you would imagine that maybe they're not getting very good filters because they're training with only 1D filters, but they reconstructed the first layer of those filters by doing matrix multiplication, multiplying those 1D filters. Like I said, then you actually can reconstruct the 3D matrix back. And that's what, and these filters are what that look like, and they've demonstrated that they show a variety of color, a variety of orientation, and complexity and frequency. So they were able to get the discriminative power that they were looking for. And the result is that really their test accuracy was the same or even better. However, they were only evaluated these methods on CFAR and MNIST, smaller data sets. And I think there's a reason why they pick 5 by 5 filters in their baseline. Because if they start with 3 by 3, then their saving is less. So if they started with somewhat of a slightly bigger filter, then their computational saving is larger. But also the issue is they don't have deep enough of a network, and they only evaluate it on a few small data sets. So that I don't think that was convincing enough until MobileNet came around. So MobileNet is a very similar idea. This figure came straight from MobileNet paper. They're demonstrating what regular convolution looks like. It's a 3D filter. That means a filter looks like a rectangular object that's x by y by depth, and you have n of them, n number of those filters to train with. But what MobileNet did was, instead of doing everything 1D, they only break it into two parts. The first part is a spatial filter. That's a 2D spatial filter, the XY filter. And then they following after that is a 1D channel-wise or depthwise filter to combine all of that results together. So this was published 2017, the first version. Their depthwise separable convolutions start with, like I said, 3 by 3 by 1. So as a 2D spatial filter followed by a 1D depthwise filter. They constructed their network to be 28 layers and a vast number of variants. They evaluated on standard data sets, ImageNet, standard Stanford Dog, M2GPS, YFCC, I think it's a face recognition data set, and also COCO. And at comparable accuracy with VGG16, they only needed 4.2 million parameters compared to 138. And I think the reason here, and that's what made everything popular, is because they've actually evaluated on standard data sets rather than small data sets. And they've constructed a sizable neural network with it instead of just a toy example of 3 to 5 layers. And they've demonstrated that this actually works. And that's how they got all the popularity. And some people would talk about why are they not using 1D filters, because you get even more savings. So my experience with it is that when you go everything 1D filter, you are going to face some accuracy trade-off. So what they're doing here is that they're trying to find a balance of efficiency and accuracy trade-off by separating it only after the spatial convolution is done, because then you capture as much as the spatial information as you can, and then only then combine them through the depths of different filters. So that seemed to work well. So some takeaways of all that we've just went through. How do we use it effectively, separable convolutions? First, we know that, well, the paper reported that the inference time is faster, but also training time. So that was also interesting. Apparently, there's around 20% faster training time that was obtained from training on ImageNet. And what's important here is computational savings gets even more with larger filters. Remember, because the complexity is based on the filter size. And originally, a 3D filter size, the complexity is cubic. And cubic drops to linear time if you make it into 1D. And therefore, if you have larger filter, you have much more savings as well. And what does that, so some examples here. If you start with a 3 by 3 by 64 filter, that drops from 576 multiplications down to just 70. 15 by 15 by 64 filter drops from 14,000 multiplications to just 94. Even larger filter, 35 by 35, 78,000 multiplications per pixel. Not to mention your image is likely 500 by 500. So, but down to 134 multiplications per pixel. So that means it allows us to build larger receptive fields that can capture more contextual information. So contextual information is especially useful for semantic segmentation, especially these days. There's a number of models using larger, well, they might have 2 branches of connections. One is progressively going smaller into an encoder-decoder architecture. The other one is taking roughly the full image scale and then skip that all the way to combine with the encoder-decoder. So that's where they get the contextual information. But in this case, you can directly get contextual information by covering a larger area with larger receptive fields. And the computational cost is no longer an issue here. And because we're saving a lot of parameters with separable convolutions, and therefore we can build even deeper and even wider meaning more filters per layer, because you're not going to explode with a huge number of parameters anymore. But just make sure you do still use residual connections to avoid vanishing gradient, because your network's going to be even deeper. And it's especially good at early layers, because another aspect of this is that the input, because you're performing convolution per pixel on an input source. And the input is the largest when you're having an image just being passed in. Image is the largest, and then it gets progressively smaller. And therefore, that's where you get the most saving, because the image has the largest input. So this works really well. Early layers, just like flattened CNN has demonstrated, even with a reconstructed filters. And all of those really, what's really great here is that you can use any of the existing frameworks, such as PyTorch, TensorFlow, Caffe, without implementing your custom layers, because they allow you to build 1D filters, right? So you can just build your network with pure 1D filters and try it out. So this is actually really easy to do, but could be really interesting for anybody's use case. And so these are the resources where I've compiled the presentation. We're also hiring a number of engineers. And so separable convolution is a big part of what makes our on-device computer vision possible, because we have to run object detection, semantic segmentation, lane segmentation, along other things all at the same time, in real time. So it has to be super efficient. And hopefully that was helpful to everyone. Thanks.
Great talk, thanks. I have a couple questions. When you're talking about the separable filter, and when you had them in separate layers, was there like an activation function between each layer, or was it just keeping it separable and then having an activation?
So we found that depending on different tasks, it worked differently. So that's where the art side of neural network happens. You just have to try for your use case. For us, we had a mixture.
Okay.
Yeah.
And then the other question was, when you have the three-dimensional ones, the convolution in the spatial one is going across, going with the stride of 1 through every pixel, but through the depth, are you actually sliding along the depth and doing a different convolution, or is that just? No.
It's just the whole depth all at the same time. Yeah.
Thanks. That's the last question.
Thank you. Very, very informative presentation.
Thank you.
I have a question about what percentage of the practicality of it, and I understand it's depends on what percentage of the real networks that are really sparable. The kernel are sparable. Because I understand that they need to be symmetric in order to be sparable.
Well, they don't have to be symmetric. So, for example, the Sobel filter was not symmetric. I think it was positive 1, 2, 1 on the left and negative 1, 2, 1 on the right. Yeah.
Symmetric in one dimension.
Well, so in order for a filter to be decomposable exactly into separable filters, that filter has to be rank 1. So rank 1 means you have one linearly independent row vector that can kind of generate the 2D or 3D matrix from that. And that's why it's separable into those 1D filters. So in theory, you would have to do upper echelon transformation to prove that those matrices are rank 1 in order to decompose them. But in practice, as what flattened CNN has shown, the 3D filters themselves, they don't really have to be rank 1, but you're able to still get pretty good approximations from just a sequence of 1D filters. And how they showed was their accuracy and their reconstruction of the visualized filters from their separable 1D filters.
So it's approximation?
It's approximation, yes,
okay.
yes, of course.
100%
Yeah, and that's why you're getting, there's a trade-off in accuracy. However, if you use it, if you don't, for example, my suggestion would be you use it, for example, in the earlier layers, where later layers maybe you use less of it. But if you use everything 1D, you're gonna lose a lot of accuracy. Yeah.
Are there cases that you cannot do the approximation? That if you are doing the sparable solution, it's not accurate? And
Sorry, can you say that again?
So my understanding, in order to do it sparable, you're doing you're losing some accuracy. are there cases that the loss of accuracy is so high that it doesn't make sense to do it?
It depends on use case. So if you don't have enough, if the accuracy loss is too much, then you want to mix in some of the non-separable ones, just regular ones. If you're finding that your network is still giving you pretty good trade-off, because usually you have a KPI you want to meet where your accuracy cannot drop until a certain point. So you can kind of play around with that. You keep changing your network until you're right around the accuracy and see how much of an efficiency gain you got there. Yeah.
Thank you.
Yeah.
Okay, maybe it's a little bit outside what the scope, but I just wonder if there is any work on the frequency domain and maintaining basically on a large filters convolution using like FFT, inverse FFT for. That's
really interesting question. I've briefly thought about it, not much, so I unfortunately won't be able to answer that very well. Yeah, but that's really interesting for sure. Great, thank you.
Thank you, Dr. Chen. And then